Today, we will be demonstrating the mechanical testing of metallic materials. We will be tensile testing two different grades of aluminium, namely a T6 and a 1050, in order to highlight how the mechanical behavior of the two different grades of aluminium differs. There are a number of different samples that we can test for tensile testing of metals, and the type of sample that we choose will depend on firstly the state of the material that we have, and it will secondly depend on the standard that we choose to use for the testing, and depending on what sample type we choose, that will influence the properties that we can measure during the test. For instance, here we have a cylindrical aluminium sample. As you can see, this sample has some distinct features, and because of these features, it is known as a dumbbell sample. Now, on the ends of the sample, you can see it has a threaded edge, and this is for a specific type of tensile grips on the ultimate tensile tester. The sample then has a shoulder with a fillet, and then it has a thinner area in the middle. Now, this area here is the area that we're interested in, and what we're trying to do is we're trying to get this sample to fail in the middle when we apply the load. Similarly, here I have a steel dumbbell sample, and as you can see, this sample has slightly different geometry to the threaded aluminium sample because this sample has been manufactured for a different set of tensile grips. We can also manufacture samples from flat plate. For instance, here I have an aluminium plate sample. Now, this type of sample is known as a dog bone because of its distinctive shape. Similar to the dumbbell samples, it also has a shoulder with a fillet, and once again, this is to ensure that when this sample fails, it should, in theory, fail right in the middle here. Now, the reason that we have different sample types, firstly depends on what state we get the material is, whether we get like a big chunk of material or whether we get the material supplied to us in a plate form. And secondly, it can also influence the properties that we measure during our tensile testing. The properties we want to measure today are the elastic or Young's modulus, the yield strength, the percent elongation, and the ultimate tensile strength of the aluminium samples we are going to test. We are going to test these samples according to ASTM E111 and ASTM E8. In order to measure the elastic modulus of this sample, we need to know the geometry of the sample. So we need to know the width, which I'm measuring here with a digital vernier caliper, and we need to know the thickness. These measurements will be used to calculate the area of the sample, which would be used in the stress calculation. I also need to know the test length or span length of this sample. Now, because this is a dog bone sample, I have to measure the distance between the two fillets, and this I will determine when I set up the test. The important components of the universal testing machine are the load cell, the crosshead, and the grips. In this case, we are using a 20 kilonewton or 2-ton load cell to measure the force that is applied to the specimen. The force is applied to the specimen through the movement of the crosshead, which can move either up or down depending on what type of test we are running. Lastly, the top grip is responsible for transmitting this movement to the specimen, whereas the bottom grip anchors the specimen and resists the movement. The force from the load cell and the displacement of the crosshead are fed into the control box of the Shimatsu, and these are recorded by the software in order to generate the load displacement curve that we have spoken about in lectures. Because we are testing dog bone specimens today, the crosshead displacement is not an accurate representation of how much our test length of our specimen has elongated. And because of this, we need to use another form of measurement device to measure this displacement. In this case today, we will be using a laser extensometer, which is a non-contact displacement measurement device. The data from the laser extensometer is fed into a data acquisition box, or DAC. At the same time, the load and the crosshead displacement from the Shimatsu are also fed into the DAC in order for me to record all three measurements simultaneously. At the same time, the Shimatsu Universal Testing Device software is recording the crosshead displacement or stroke and the force that the load cell is experiencing in order to generate a load displacement plot as shown here. I have now loaded the specimen, which is a T6 aluminium, and we are now ready to start our first test. As you can see here, the initial part of the course of the curve is linear, and this indicates that the material is still in the linear elastic region and is still elastically deforming. If I remove the load here, the material would return to its original state and there would be no signs of permanent deformation. We can now see that the behavior of the material has gone from linear elastic to non-linear, and this indicates that the material has now yielded. The graph is now showing that the material is undergoing plastic deformation. This plastic deformation will continue until the ultimate tensile strength of the material is reached, after which it will neck and fail. The ultimate tensile strength of the material has now been reached. It will now start necking and will fail shortly after. The material has now failed. We will now test an aluminium 1050 specimen and compare its behavior to the T6 we previously tested. As you can see here, the 1050 specimen is also showing elastic behavior initially. However, it is a lot less stiff than the aluminium T6 sample as judged by the slopes. We can also now see that the 1050 sample has gone through the elastic region, it has yielded, and it is now experiencing plastic deformation. But the yield strength is a lot lower than the aluminium T6 sample. The 1050 has now reached its ultimate tensile strength and it has necked. The 1050 yielded at about 5.5 kilonewtons, whereas the T6 yielded at about 13.8 kilonewtons. So here we have our failed T6 sample compared to an unbroken T6 sample. As you can see, the failed sample has plastically stretched an amount. When we examine the fracture surface of the T6 specimen, we can see that it is very flat with very little plastic deformation, and this is indicative that the T6 failed in a brittle manner. So here we have the 1050 specimen before and after testing. Once again, we can see that the specimen has plastically deformed a small amount. However, when we examine the area where the failure occurs, we can see evidence of necking as well as a lot more plastic deformation than occurred on the T6 specimens.